Okay, fine. We are going to look at sets and set theory. This is a
Okay.
very important topic for everyone who does pursue the subject of mathematics. Okay, because it helps us deeply understand the relationship that may exist between various components which we are going to deal with, particularly variables. Okay, so that's
Okay.
how it is.
Okay.
Okay, fine. So to start with, we start by looking at the definition of a set. Okay, so as
Yeah.
simple as it looks, you'll be asked to get an understanding of what a set is, which can only be defined as a set, as a collection of well-defined objects. Is a collection of well-defined objects. These objects are aptly known as elements or members of a set. Okay, elements or members of a set. Normally, a set is indicated or denoted by uppercase letters, capital letters like A, B, C. So you can say set A, set B, set C. And then the elements which are members are normally represented by lowercase letters like A, B, C, D, etc. Okay, so that's the standard.
Okay.
Okay, that is the standard. Okay, please mute your mic unless you want to ask a question. Mute your mic. Okay, okay,
How do
fine.
I mute?
I'm saying switch off your mic. Okay, fine. Unless you want to ask a question, that's when you switch it on. Okay, great. So what is the set notation? Okay, uh, normally the sets are noted by use of curly brackets. As you can see, you have set A, which has got three elements: element 1, element 2, element 3. To show that it's a set, you put them in curly brackets. Okay, so that's what it is. If an element belongs to set A, we write in this manner x with this Greek letter. Okay, here, that's how we write x belongs to A. Okay, so if it doesn't belong to A, we write with this cross here on this Greek letter to show that x does not belong to A. So that's how it is done. Okay, so we proceed. We look at the what we call set equality. Okay, set equality. It won't surprise you to note that we can also equate two sets. We can equate two sets. Two sets are said to be equal if they have the same elements or same members. Okay, for instance, if you have set A, there you have set A having three members, 1, 2, and 3, and set B also having three members, 3, 2, and 1. The equality does not depend, is not going to be looked at in terms of the same order in which the members are arranged. You can see you have 1 starting under set A, followed by 2 and 3. Then set B, you start with 3, 2, and 1. But they are identical items in A and B. That's what marks them to be taken to be equal sets. Then we talk about cardinality of a set. Okay, cardinality of a set is simply representing the number of elements in the set. So when you hear of cardinality of a set, you are trying to find out what is the total number of elements in the set. That's what we talk about as cardinality. So the cardinality is indicated by putting two parallel lines between the letter which is representing the set. Right? In this case, we have parallel line which are sandwiching the letter A we have first parallel line, then A, another parallel line. Okay, so that shows the cardinality of a set. So in this particular case, set A, the cardinality of a set in this case is 3, because their number of members is 3. So the cardinality of set A is 3. Also cardinality of set B is 3, because the members or the number of elements is 3. Okay, so we also look at equality of set in this manner. As I've said, is not dependent on the order. What is important is do you have identical items or identical members in both sets. So if we can look at the mathematical statement, we can write it in this way to say if all A belongs to A, in this particular case, you can see this one is all A belongs to, this symbol indicates belongs to. Okay, belongs to A, and A belongs to B, and for all B belongs to B, and again B belongs to A, then A is equal to B. Okay, so what are we saying in this case? What is being shown here is that in the first case A belongs to A, there is A here. Then again A belongs to B, there is also in set B A here. Then B belongs to B, there is a B here which belongs to B. And then B again belongs to A, there is B here which belongs to A. So we can see that in set A there is A and B, and set B there is A and B. Therefore set A is equal to set B. So that's what we look at. Okay, that is what we look at. We proceed in this manner, more explicit, looking at what we mean by equal set. As I said, it's not about the number of elements, but the composition. Okay, are there identical numbers there? So here we have under set A 1, 2 and 3. Under set B there is 1, there is 2, but 3 is repeated multiple times. Okay, but what is important is for us to relate. Is there 1 here and one in the other set? Yes. Is there 2 here and 2 in the other set? Yes. Is there 3 here and 3 in the other set? Yes. So if these are matching, then we say these are equal sets. So A is equal to B. Okay, so that's what we look at. Okay, then let's look at the other one. If we talk about types of sets, types of sets, we have one which we call empty set or null set. A set without any elements is denoted by the symbol, Greek symbol phi. Okay, that one, the Greek symbol phi. Then we have also a finite set. That's a set with a countable number of elements, a number of elements which you can count. Okay, so that is a finite set. We also have an infinite set. So the set with a number of elements such as natural numbers, you can continue counting them. It goes to infinity. You can continue counting them. So we can say that is an infinite set. Okay. Then we also have a singleton set. A singleton set refers to a set with only one element. With only one element. That's what we call a singleton set. We also have what can be referred to as subset. Okay, a subset is a subset. A set A is a subset of another set B, for instance, if every element of A is also an element of B. This is denoted by this symbol. Okay, subset A is a subset or equal to B. So there are some literature will show this symbol. Others will show without an equality down there. Okay, but generally this simply reads A is a subset of B. Okay, so that's what we have on that regard. So diagrammatically, this can be demonstrated by this. This is a subset. You can say subset. Okay. Okay. So meaning that every element of A is also an element in B. So A is a subset of B. That's what it means here. A is a subset of B. So that's what it means. Okay. Now, when you look at this, you can further illustrate it in this manner, where you have A with three elements, 2, 4, and 6. Then you have B with 6 elements, which is 1, 2, 3, 4, 5, and 6. You can see that every element of A is also found in B. Therefore, A is a subset of B. So that's what it means here. Okay? We move on. Look at this one, another mathematical statement. We can write it in this way, that if A is a subset of B, if A is a subset of B, but A is not equal to B, that's what the mathematical statement reads there, then A is a proper subset of B. Okay? A is a proper subset of B. Okay? So that's what it means. Okay? Okay? So now, why is that sometimes emphasized? Okay? As I said, in some other mathematical literature, when writing the subset, they will say A with this letter without an equality sign down there as a subset of B. Okay? Meaning that it could mean that A is equal to B, or if without an equality sign, you can say A is a proper subset of B. Meaning that A number of elements are fewer than the number of elements in B. Okay? So that's what it can mean, a proper subset. Now, you can have a situation whereby A is equal to equal to B rather, means that the same type of elements in A are found in B. Then A is a subset of B, or A is equal to B. That's what it is. Okay, so in this case, we are emphasizing that A is a proper subset of B because A is not equal to B. Okay, so that's what it is reading there. So again, you can further extend it by looking at it in this way. If A is a subset of B and B is a subset of C, then always A and B are part of C. Therefore, you can say A is a subset of C as well, as demonstrated in this graphical presentation. Okay, so that's what it is there. Okay, so it's important to get an understanding of how these sets are denoted. Okay, it's very important to understand how these sets are denoted. Okay, so we move on to look at another type of set, which we call a universal set. These are terminologies which will be confronted with as you deal with sets. The universal set is simply one that contains all elements under consideration in a particular context. Okay, so that's what I've said there. Okay, that's a universal set. It is a summation of all elements to be considered, in other words. Okay, that's what we call a universal set. We also have one that is referred to as the term which is referred to as complement. So you can have a complement of a set. Okay, a complement of a set denoted by several symbols. Some of them which I've indicated are here with S with an apostrophe like that, or A with a heart, or A with a bar on top. They are all indicative that you are talking about a complement of a set. This complement consists of all elements in a universal set that are not in A. That's what the complement is. So all elements in the universal set outside the set of A, in short. That's what we call a complement of a set. Okay, so we look at the universal set in more detail. A universal set is a set that has all elements that are being considered in a problem. If you are talking about, for instance, a research, you could have taken your interest area, and all those areas that can be taken into consideration will be taken to be a universal set. But definitely what you do is you might not consider everything, you might get a sample, so you have a subset of a universal set to consider. Okay, so that's what it is. It is often shown using a symbol in this particular case. Okay, these are the symbols that you need to be familiar with to represent that this is a universal set. Okay, that's how it is. Okay, now we also have in this particular case a demonstration by way of a Venn diagram. The universal set is indicated by a rectangle around the sets. Okay, the universal set. So this is a limitation. Okay, this periphery. Okay, these boundaries. Okay, drawn in this manner is what is a depiction of a universal set, because it closes in everything that is under consideration. All the elements under consideration. So that is the universal set. Okay, as demonstrated here, in this case, all the elements under consideration are 1, 2, 3, through up to 6. Then you have A. Set A has only 3, 4, and 5, whereas set B has only 5 and 1. Okay, 5 and 1. Of course, this is we can start talking about complements of a set here. We can talk about intersection of a set. We'll look at that in due course. Okay, so that's what we look at. Okay, so here we are. So we also need to look at set operations. Okay, so set operations. So there are certain symbols that to be familiar with. You should be familiar with to indicate certain particular set operations, like union set. Okay, there's this symbol in parentheses. The union set of A and B means that it's a sum of elements in A and B, denoted as A union B. Contains all elements that are in A and in B or both. Okay, so that's what we call union set. Then we have intersection set. Okay, intersection set. So this is the set of elements found in both sets. Okay, so if you are talking about set A and set B, okay, denoted as A intersection B, as indicated here. Let me just pull it out. Okay, okay, A intersection B contains all elements that are in both A and B. Let's get back to this one we just looked at. This one. If this is A and B, then you're talking about what are the intersection of set A and set B. So there is 5 in 2, there is 5 in B, there is also 5 in A. So 5 is the intersection set, the set which has one element in the intersection, okay, which is 5. That's what we mean there. Okay, so let's look at the other one, which is difference. The difference of sets. Let's look at A and B. Okay, if these are the two sets A and B, then denoted as A minus B. So contains all elements in A but not in B. Okay, all elements in A but not in B. So when we look at this particular example that I've just looked at, okay, if they say A minus B, so all elements in A not in B, that will be 4 and 3. Okay, all elements in A not in B, that will be 4 and 3. Okay, so that's how we look at it. Okay, then let's look at the other one, which is complement. The complementarity of a set. Okay, denoted by A complement, as I've already shown you the symbol, contains all elements not in A but in the universal set. So if you look at this one, okay, you look at this example. If you say what is the A complement, means that you are talking about all elements which are not in A. Okay, so what are the elements which are not in A? There is 6 here, it's not in A. There is 1 here, it's not in A. There is also 2, which is not in A. So that's what we call A complement. If you are talking about B complements, you are talking about all elements that are not in B but can be found in a universal set. So B complement will exclude 5 and 1, leaving 2, 3, and 4. 2, 3, 4, and 6. That is B complement. Okay. So then we also have Cartesian product. Cartesian product. So when you hear of Cartesian product of sets, Cartesian product of sets A and B, denoted as A multiplied by B, is a set of ordered pairs. Okay, where the first element form A and the second element form from B. First element form from A and the second element form from B. First element from A, second element from B. So that is Cartesian product. Okay, so we're going to look at that. Okay, when you look at what I've talked about, I've already mentioned the union of an intersection of set. The union is a summation of elements of A and B pictorially using a Venn diagram. That's how you demonstrate. And the symbol for union is A union B, like that. Then A intersection B, you have what are the elements common to both sets. So in this case is 3 and 4. That's the intersection. Okay. Then I talked about the difference of sets. I think just to belabor that, this Venn diagram demonstrates that if you are talking about A minus B, you are talking about all elements in A which are not in B. So elements in A which are not in B. So which is 1, 2 are the ones which are A minus B. When it comes to B minus A, we are talking about all elements in B which are not in A. So A has these. So what are left out is 5, 6. Those are the B minus A, as already explained. Okay, so that's what we have. We move on to look at what we mean by complement of a set. So complement of a set. So A complement, for instance, is all this shaded part because it's not part of A. All the elements which are not part of A are complements, A complement. That's what it means. Okay, so there we are. I also bring to you the Cartesian product. As I said, Cartesian product of two sets A and B, denoted by A times B, is a set of ordered pairs AB, where A belongs to A, this small letter A belongs to set A, and the small letter B belongs to set B. So if you have A, Cartesian product A and B, you are going to have AB such that A belongs to B and B belongs to A, small letter A belongs to B, to A, and small letter B belongs to B. So example we demonstrated here is A is equal to AB. So set A is made up of 2 elements A and B. Set B is also made up of 3 elements 1, 2, and 3. So if you say A times B, or you want to find the Cartesian product, then you are going to pair it in this manner. A to 1, that's the first one. Then you have A to B, to 2 rather, that's the one. Then you have exhausted the first one. Okay, you have also A to 3, so A3. Okay, then you have, start with B now. B against 1, that's B1. B against 2, you have B2. B against 3, that is B3. So with in curly brackets, that will be the Cartesian product of the sets, two sets. That's what it is. Okay. Okay. So now we look at the next one. We talk about laws of set theory. Okay. These are important laws of set theory. Okay. So a number of laws are supposed to be followed. Okay. You have associative laws. Okay. Associative laws, you can look at that symbolically. Associative law can be demonstrated like this. From what you have seen here, you have A union B union C is the same as A union B union C. Okay. And also A intersection B, everything intersection C. The same as A alone intersection the B intersection C. So that's what this is trying to demonstrate as the Venn diagram. Okay. We have in this particular case A union and then A union B intersection C. A union B intersection C. Okay, so we are looking at this A in the blue here, okay, combined with what the intersection of B and C, this blue part. So when you overlay it, you find that you give you this red coloring. Okay, that is what it means. That gives you the red coloring. Okay, so that is a demonstration of associative law. Okay, it can associate in this manner. Okay, so we also have next one. We look at this distributive law. Okay, you literally distribute this into what is in the brackets. Okay, in mathematics, when you are given a mathematical statement of this nature, you look at what in the brackets first. So we have A union, then B intersections. So you have A union B and A union C. So whenever you have and in between in mathematics, simply means multiply or intersection. So that's why you have this symbol here. Okay, so it is A union B intersection A union C. And on the other one, you have A intersection B union C. So you distribute it, you have A intersection B union A intersection C. So you are distributing. Okay. You also, in this particular case, before I go that, you have root 1. So A union B. So the sum of elements in A and sum of elements in A and B is shown by the shaded blue part here, and then A union C is the sum of elements in A and C, shown by this blue part here. Okay, so what is the common point between these two unions? Okay, what is the common point? So if you have to overlay, okay, what can be double coverage, or what can overlap? Okay, what can overlap? You can see that A is here, there is also A here. So the whole red A here is covered. Okay, then you have this part which is A intersection C complement B. This part is also covered here. Okay, then you have also A intersection B intersection C. This part is also covered here because it will be overlapped. Okay, so and then that's all that is there. Then apart from that, there is this part which is A intersection C complement A, which is this part. It's also covered here. So you find that when you put this on top of this one, there will be an overlap in this shaded plus. So this is what the distributive law of set theory will indicate. Okay. So we go on to look at the next, which is talking about we are talking about commutative laws. commutative laws. So that tells you that A union B is equal to B union A. So commutative law simply indicates to you that you can carry out the operations and despite you swapping the elements, the result will still be the same. Okay, you can swap A. Here A is the first, B is the last, but you still be going to show you the same result if B starts and then A becomes last. Equally for multiplication or intersection, you can start with A, then end with B, but the result will be the same as if you start when you start with B and end with A. So that is what the commutative law implies. So let's look at the diagrammatical presentation of commutative law. Okay, so you can see here you have commutative law here. You have the first one has 6 elements, then the next one has 3 elements. So if you sum them up, the union of these two will be 6 plus 3, it will still be 9, which is the same as if you start with 3, then sum up the next 6, it will still be 9. 3 plus 6 will still be 9. So this is indicative of commutative law. Even multiplication, you can look at this one, 4 rows by the order of 4 by 2, which is 4 times 2 is equal to 8. The same as the order of 2 by 4 will still be 8. Okay, so that's what is showing there. Okay, I also have the other one, which is known as the idempotent law. According to idempotent law, a variable odd with itself will always be equal to that variable. Okay, A plus A equal to A. A variable and with itself will always be equal to that variable. A times A is equal to A. That's the implication. Let's look at this one. With this one, A, so A is 0. So 0 times 0 is to be 0. So 0 times 0, this point dot is simply saying is a 0 times 0, it's still 0. 1. 1 times 1 is still be 1. So that is the idempotent law. That's what it tells us. Okay. We have also De Morgan's law. Okay. In set theory, De Morgan's law. So what does this De Morgan's law mean? So when you look at the diagrammatical presentation, it's showing you that when you have A union B, okay, A union B, it will be the sum of A and the sum of elements in B. Okay. Now when you look at this one, it will tell you that A union B complement. Okay. So A union B complement, which is this one, the all red blue shaded part inside there, is equal to A complement intersection B complement. So let's look at this one. Let's look at this one. Let's look at this. Okay. So what does this mean? We have A union B, fine. So what is A union B complement is this shaded part outside these two circles. Okay, that is A union B complement. Now when you look at individually, A complement is anything outside A. So meaning that it takes this whole part outside A. What of B complement is anything outside B. Now where do these two meet? It still goes back to the green part here. Okay, so that's what it means. So that is what this mathematician De Morgan's law found out some time back. Okay, so I can further illustrate this one by looking at this example. So De Morgan's law provides an easy way to find the inverse of Boolean expression. Okay, so when you have x plus y, okay, complement, is the same as individual x complement and y complement multiplied by y complement. So when you have x multiplied by y complement, is the same as individual x complement or y complement. An easy way to remember this in this term is each term is complemented is that or becomes and ands become ors. In even in probability, where you have or you add, where you have and you subtract, where you have or is like union, where you have and is like intersection. Okay, so that much you should know. So to the complement of the product is the sum of complements. Okay, to the complements of the product is the sum of complements. To the complement of the sum, the first one here is the product of complements. That is De Morgan's law. Okay, then we talk about the Venn diagram. Okay, now Venn diagram is simply a presentation that is used to illustrate relationships that are between sets and their operations. Okay, in other words, we can also talk about Venn diagrams, which was created by John Venn in 1880. Okay, that way back. Through them, we are not then attacked. They were not called Venn diagram until Clarence Lewis, in his books which he published in 1918, started to call them Venn diagrams. Okay, so that is the simple information that you can be required to know about the set theory and applications. Okay, so in sum, I can say that sets and set theory form the basis for various mathematical concepts, including functions. So later on, when we look at other slides which are coming in future, we'll start realizing that this information is very important because we tend to relate certain variables using these set theories. They will help us to calculate. Also, we look at this set theory being used in probability, okay, or in combinatorics. Okay, those are also very important. Combinatorial functions also use set theory. Okay, we also note that set theory is extensively used in computer science, statistics, and engineering. That is a fact. Okay, and also it's important to understand sets and set theory, being them as crucial, being crucial mathematical disciplines and the applications. Okay, they are crucial in mathematical discipline and applications. Okay, so that's how it is. And also the set theories is going to assist you to understand some complex mathematical problems and how we analyze complex data, so using set theory. So that's what you should understand. So thank you for listening. Please done this to help you to understand the future mathematical issues. Okay, so until we meet next time, unless there are other questions, we end here. Are we together? Are we together? Okay.